In this video here, we're talking about Gauss's law, and in this video in particular, we're going to talk about the right-hand side, this side over here. We have another video up which sort of introduces the general features of Gauss's law, and another one addresses the left-hand side. Well, on this side, we're talking about the right-hand side. So the right-hand side is sort of, there's a constant here that we're not really going to talk about, just epsilon here. You just have to remember to divide your left-hand side by it as you use the law, but there isn't really much to discuss here. So the real thing to discuss here is this Q sub E, which stands for charge enclosed. Hopefully you sort of got the general gist of Gauss's law now, that you choose a surface, a closed surface, that's what the ring means on the integrals here, that encloses the charge that's generating your electric field. And now the question on the right-hand side is, well, okay, fine that you're enclosing some charge with your Gaussian surface, you handle that on the left-hand side, but how much charge are you enclosing now? That's what QE is. That's what you have to figure out, how much charge is being enclosed by the Gaussian surface. So about the easiest case you can think of here is a case where you just have a point charge like this, and of course you have your electric field lines going out in all directions like that, and you surround it with a Gaussian surface like this, and it's quite simple to look at the Gaussian surface and go, okay, how much charge is enclosed by this purple curve? How much is inside here? It would just be the value of this point charge here. Maybe it's an electron, so you have minus 1.6 times 10 to the minus 19th, or maybe it was stated to be 10 nanocoulombs, but in either case, that's the amount of closed charge. Pretty simple to get. But where it becomes more difficult then is if you have sort of a more sophisticated system, like say maybe a line of charge like this, where the line of charge is totally stacked with charges like this. And now, because of the cylindrical symmetry of the system here, I'm going to go ahead and put a cylindrical Gaussian surface around it. Looks like a toilet paper tube. Maybe something that looks like this. There we go. There's a cylindrical surface here. And I've just chosen the length of this to be L. That's my choice right here. The person sitting right next to you might choose a different dimension, whatever. But the issue now is, well, how much enclosed charge do we have now? How much charge is enclosed by that green cylinder? If you choose a longer Gaussian surface, there will be more charge enclosed. A smaller Gaussian surface, less charge. And you also have to wonder, well, what is the charge density of this thing, the lambda of this thing, in coulombs per meter here? If it's a very large charge density, there will be more charge enclosed by the equivalent Gaussian surface relative to if it was a smaller charge density. So there's a lot of questions like that in computing the enclosed charge. Now, probably the easiest way to think about this, the enclosed charge, well, the enclosed charge, for this case here, actually will just be lambda times L. That's a pretty simple-minded idea here. It's the coulombs per meter times the meter. You see, if you multiply them, units will come out to be coulombs. And that's not a bad way of thinking about it. And in this case, in fact, it would work. But one of the problems then is, like, what if lambda here was, say, not a constant? There are problems out there that you might encounter where lambda is some function of something. Like we might have a particular charge system where maybe the charge is very dense on this side, but then it starts to lighten up as you go out. So very dense, and it starts to lighten up like that. So, in other words, lambda is a function of position. How much charge is enclosed in that case? This relationship won't do it properly if lambda is a function of position. So the way you should think about enclosed charge is something like this. The enclosed charge to you should always be in the form of an integral like this. It should be something like lambda dx if it's a one-dimensional case. Or if it's a two-dimensional case, it should be something like sigma times dA, something like that. And if it's a three-dimensional case, it should be three integrals of rho times dV, something like that. These are the cases that you can never get mixed up if you do it this way, because what you're doing here is you're allowing for the consideration that lambda might be a function of the variable of integration, or might be a function of the spatial extent of the object itself, might be a function of x for the rod, might be a function of the area for, say, a two-dimensional, like a plane. In this case here, you might have a plane like this, a charged plane, where maybe the charge is really, really dense right here, but it lightens up as you go out to the outer sides like that. So as a function of a two-dimensional going along x and y, you sort of sample a different charge density as you go. And these pop up a lot in the elementary physics textbook here, where rho is not a constant. So in this case like this, you might have a sphere like this. So a sphere that looks like this, and the charge might be packed on really, really dense right here at the center, but might get all a lot lighter as you go out to the edges, or the opposite, or anything in between. Any bizarre charge distribution will be handled properly by these relations right here. And just to show you how this one works right here, suppose lambda is a constant, the way I'm claiming it was right here. If lambda was a constant here, then you could pull it out in front of the integral here. You just get the enclosed charge as lambda times the integral of dx. And now you know if your rod exists, say, from 0 to L or something like that, you will just get lambda L for this, and that's exactly what this relationship is right here, just lambda L. So if the charge densities are constant, you do have an easier time, but these are the better route, at least to think about as you approach the problem, so you don't sort of use them a bit erroneously as you go. So what happens next then is that these are sort of your relations here for how much charge might be enclosed. These are the ones you should definitely think about using here for handling the enclosed charge for your Gauss's law problems. Now, if the density is constant, sure, go ahead and pull it out front of the integral like that, and you're left with an easy case there. But if they're not, then you have to leave it in. So the last part of what we'll do in this integral then, in this video, is we'll go ahead and look at what things could happen here in the 1, 2, and 3-dimensional cases insofar as these dAs, in particular these dVs, go right here, because they can sort of cause some problems as you go. Okay, I think we'll look in particular here at this last one right here. Now, what do you do for these dVs here? So if you're faced with a 3-dimensional case here of 1, 2, 3, and an integral of dV like that, oops, put a rho in there, a rho dV like that, how do you handle these cases here? Well, there's 3 types of geometries that you have to be concerned about with your dV. There's Cartesian. In a case like that, the dV is pretty simple here. It's just dx, dy, dz. So what this says here is that if you have some big charge distribution, I don't know what it's doing, but you're using rectangular coordinates, a very little bit of volume of an otherwise larger rectangle that you might have to integrate over like this just has a width here of dx, I guess it'll be dy and dz like that. Little volume like that is what it is in Cartesian. So just a little differential cube. Charge is a bit harder then, or a bit different if you get into cylindrical coordinates. Cylindrical coordinates like that. Your dV then becomes something like r dr dz d theta. That's what this would become here. So this r dr here, this typically goes from 0 to r, the radius of your cylinder here. This dz here, this is typically has to do with the length of your cylinder here. And this d theta here, this often is just integrated from 0 to 2 pi or something like that. That's the part that goes sort of circularly around the cylinder to give you that angular dependence in there. If you have a spherical case like this, which are the most common ones in physics books and that sort of thing, the dV in this case here is going to be r squared times sine phi dr d theta d phi, something like that. This is the differential volume in this case here. And these things are better pictured, say, on, Wikipedia or in your calculus book or something like that. But what we're talking about here in this cylindrical case here is if you go up here and you're concerned with just a little segment of volume of the cylinder like that. And in the spherical case right here, you can have a sphere like this here, and now once again, you're just concerned with a little bitty segment of volume of the sphere like that. These are the equations that tell you how much volume is in a little differential dV here that, of course, when you add together, gives the total volume of the object in there. And so for this thing here, the cylinder, which you just did, the r here, is, of course, goes from 0 to r, or wherever your charge distribution happens to be. That refers to the radius of your object here. The phi here is the azimuthal variable here, and so this one here is going to go from 0 to pi. And then, of course, the last one here is this theta variable here. Phi goes from 0 to 2 pi, and theta here goes from 0 just to pi. So this is sort of the polar angle right here. This is the azimuthal one right here, 0 to pi. And so all told, you can start putting these together to get the differential volume to come out. So in the case of this one right here, oftentimes in the physics problems that you work with here, the charge density, say you're confronted with trying to find the enclosed charge here, you have 3 integrals, a 1, 2, 3 like that, and suppose you put the rho in there and you're doing spherical coordinates. Here's your dV in here, r squared sine phi dr d theta d phi, something like that. You put all these things together in here. Okay, d phi is the one out here. That one's going to run from 0 to 2 pi. D theta is the inner one. That runs just from 0 to pi. And the inner one here, the r integral here, runs from the extent of the charge distribution you're talking about. You'll have to be careful with the limits. It might be something like 0 to r. But be a bit careful with these limits here of the r one anyway, because you usually have to adapt that to the problem you're working. But now if the rho variable here does not depend on either phi or theta, then what you can do is just do these integrals directly here. And what you'll find out is if you integrate from 0 to pi of d theta, that just generates a pi. And if you integrate sine of phi d phi from 0 to 2 pi, that just introduces another factor of 2. So if you sort of work through this thing here, your enclosed charge will be 4 pi, and you will be left with the integral from 0 to r of rho r squared dr. You might still have to work out that particular integral right here, but the 4 pi is completely worked out by doing the theta integral and the phi integral to get all that to go. And so the reason why we're leaving in this form here is because look at your textbook problem. You have to look, is this rho here a function of r? If it is, then you cannot pull it out of this last integral right here. You have to leave it in so you can actually make that integral work out. And that's where a lot of the problems come with. The students attack these problems here, because oftentimes they're too eager to pull the rho out of these integrals, forgetting that rho might very well be a function of some of these variables of integration. So you have to be careful about leaving it in there, and just be double careful about not walking around with these Gauss's law problems saying, oh, the enclosed charge though is something like rho times v. That's what this integral would eventually give if rho was a constant. But if it's not constant, you have to stick with some calculus here and be careful about how soon you pull the rho out of the integral.